Okay, now we'll give you some corollaries of this analytic form of Banach theorem. This analytic form of Banach theorem. First corollary. This one of this process. You can this corollary tell us that you have this solution, and you also know G is the linear subspace of E, this kind of function, and in the same condition you have this. You can prove that there exists f which is linear of this one, such that the norm of f is equal to the norm of J. This one, the norm is E star, this one is the norm of D star. This kind of function is very simple to prove. It's a linear subspace of E. You have this condition. For the proof, you just consider this norm. Let us consider that P of X, the norm of J. This one. If you take P of F like this, you can get very easy for this one. Notice that I put equal that this is just kind of function. And from here we can prove easily using the fact that this one verifies already the function. This one. If we first of all the residue in J is equal to J, that means that the norm of J in E star is necessarily bigger than the norm of J, because F is an extension of G. So we have this condition already. Can put it one there. And the second condition, the second trick, if you compute the norm of this kind of map or period, you know that f of x is also big less than the norm of x. This kind of function. This one is the p of x you consider. Then from here, the norm of f, which is equal to the subnorm of the norm of f of x, the norm of x less than 1 will be less than the norm of J, using this fact in the body. So from here, and from here, you have this kind of quantities, but also very simple to prove this one. From here to here, you have this one, and those is equal. Donc, if J is linear for you, you have to use the Banach theorem. You have to prove that the norm of F is necessarily the norm of J. The norm of F is a norm of J. The norm of J is exactly the norm of the extent function of J. Corollary to this one. And for x0 hypothetic E, you can get f which is also an element of the dual, such that you have this condition, the norm of f must be equal to the norm of x0, and the norm of this one x0 must be exactly equal to the norm of x0 square. I will denote this function is exactly the same. You can go to f of f0 of x0. It's just a notation. You'll see that many books, you see the writing f of s, you see also, you see the f of s, you can write the f of x like this. It is same. It's just a notation. Here is the duality form. This f is the dual of e. This one is the e. This form is very clear now. This one. You see that this one is the dual of e. This one is the space. So it's very clear to understand like this. So just a corollary is very simple. Use this fact also to this kind of function, which is very simple. And the third corollary, if you don't understand, you can have some problem to have the proof, tell me. I will give you the proof after. If not, just simple, just trivial application of the definition of the assumption of the theorem, the Banach, the analytic form. Corollary. 3. We just prove that for all x in E, the norm of x will be equal to the supreme of f for E when the norm of f less than 1 when f element of the integral of this. Very simple. Very simple. For the proof, I give you a sketch of the proof of this one. We just consider the fact that using this conversion, you have this one. You know that f for x is equal to the norm of x square. That means that the f composite with the norm of x like this is exactly x must be equal to the norm of x, this one. And you know that obviously that this kind of function using this fact, the f for quotient for the norm of this is an element of the ball, the unit ball of this one. The unit ball in the dual space, this kind of function, this called. So that means that the supplement will be bigger than then the supplement of this kind of function is bigger than this one. Then which will be the norm of x. Then the supplement of the norm of x is bigger than this kind of. I'll write the supplement. Then the supplement of f of x, when you have this condition, this one is bigger than the norm of x. It's bigger by the norm of x. Use the fact of this one. Also, you say that you know that the f of x is the norm of f. The norm of x like this. You can use this kind of function. That means that the support of f of x, when this one is like this, you don't need to put this one. When the f, the unit ball of each one necessarily must be equal to the norm of x. So when you use this part, and this part, you have our equality. This one and this one will be equality. Just this one is just a consequence of the corollary one and the corollary two. This one. Okay. You have another theorem, another corollary of this kind of function. But maybe you come after to prove it, this kind of function. This kind of theorem is like this. You can put it like corollary 4. particularly for in the same condition, you have to prove some. When you have C, which is a convex, you consider phi, which is a closed set, and which is not contained like this. Let's see a convex and open. Say that x0 is not an element of C. At least this one. But x0 element of E, which is not necessarily not at E. This one is convex, is open, just all. And then there is this function, this guy. Then there is this f which is not equal to 0, which is the dual of this one, such that you have f of this one less than f of f0, this one. When for all x in C, with our convex, you are just conditioned and you have to this. You use this one to prove the geometric form of Banach theorem and so on. So the next part, of course, I will define the geometric form of Banach theorem and so on. We put it very, very simple. Okay. In the beginning, before giving you the geometry form, I'll give you the definition of hyperplane. You see that H is a hyperplane. H is of E. That H is contain the element like this form is like this, such that f for x is not equal to alpha. This kind of, then you call this one the hyperplane of this one. And we can notate that we can just this one in the f is equal to alpha. When f is the linear map of f, which is not necessarily continuous. You have this call it the hyperplane. And when the case when the dimension of this one is n, just the dimension of the dimension of h is just minus 1. That you are in the finite dimensional, the codimensional of h is exactly 1. Is this kind of called this kind of function. Not so they contain f less than this kind of function. And then you have this the dictator, which is very important to say that each actor here is this one is closed. Is if only this one f is continuous. If this will close, then f is continuous. So the proof the proof is also trivial. Said if suppose that if you want to propose this one, first of all, if f is continuous, if f is continuous, then f minus 1 of the singleton alpha, which is equal to exactly h, is closed. This is because f is continuous, the inverse image of closed subset is closed. This one is closed because R is a Hausdorff topology. So any singleton is closed. Though this one is closed, the inverse image is also closed. You have to get in your mind that when you have a Hausdorff topological space, any singleton one is closed. Then this one exactly This one is called the inverse image of